Hi, my name is Allison Barkdull, and I'm a third-year biomedical engineering student at the University of Florida. I will be presenting on the adsorbent properties of three different polymers of intrinsic microporosity. Industrial gas separations, such as natural gas treatment, use significant amounts of energy, between 10 to 15% of the United States' total energy consumption. Therefore, it is important to develop novel materials capable of conducting these gas separations with lower energy requirements. Polymers of intrinsic microporosity, which I will refer to as PIMs, are a promising family of adsorbent materials for these applications. Molecular simulations allow us to calculate adsorbent properties, such as the loading of a variety of industrially relevant gases and gas mixtures. Here, I show the structures of the three PIMs examined in this study: PIM-1, PIM-TMN-Trip, and PIM-TMN-SBI. Notice that all three structures have rigid ladder-like backbones. PIM-1 and PIM-TMN-SBI have spirocenters, and PIM-TMN-Trip has a bridged bicyclic ring. These molecular features cause the polymers to pack together inefficiently. To use a metaphor, we can picture the polymer frameworks as being similar to a block of Swiss cheese. A block of Swiss cheese has holes, but in the case of a polymer framework, it's shrunk down so that the holes are microscopic. We refer to those holes as pores, and they are represented in the fractional free volume, which tells us the amount of empty space in the polymer, and this is what allows so much gas to adsorb into the framework. We obtained three PIM structures from previous work and simulated gas loading states into these structures using Monte Carlo sampling in the RASPA software package. Monte Carlo sampling allows us to calculate energetically favorable gas loading states within rigid polymer frameworks. Gas loading was evaluated at a temperature of 300 Kelvin and pressures ranging from 0.1 to 30 bars for a variety of industrially relevant gases and gas mixtures. In those simulations, the polymer framework is held rigid. However, in reality, polymer frameworks rearrange in response to adsorbate molecules. To assess this aspect of adsorption, additional simulations were conducted, combining the Monte Carlo sampling I just told you about with isothermal isobaric molecular dynamics simulations. In molecular dynamics simulations, no new adsorbate molecules are added to the framework. Instead, the framework is allowed to rearrange in response to the previously introduced gas molecules. Here, I display the results of a GCMC simulation of methane adsorption in the three PIM frameworks. On the y-axis, we have loading in millimoles of adsorbed methane per gram of PIM framework. On the x-axis, we have pressure in bars. We can see that gas loading increases with increasing pressure. When comparing the three frameworks, we see that PIM-TMN-Trip exhibits comparatively higher gas loading due to the larger available pore space. Next, we have the results of a GCMC simulation of PIM-1 alone adsorbing three different pure gases: methane, carbon dioxide, and nitrogen. Of the three gases, carbon dioxide has significantly higher adsorption, followed by methane. This indicates that PIM-1 has the highest affinity for carbon dioxide. In my next figure, I simulate gas mixtures in PIM-1 alone. The 33 to 66 nitrogen to methane and 10 to 90 carbon dioxide to methane mixtures represent natural gas, and the 15 to 85 carbon dioxide to nitrogen mixture is used to model flue gas. The mixtures containing carbon dioxide show higher loading, implying that PIM-1 selectively adsorbs carbon dioxide. Finally, I compare the rates of pure gas loading in PIM-1 across GCMC simulations, which hold the polymer rigid, and MCMD simulations, which allow the polymer framework to rearrange. The filled-in circles represent gas loading in the flexible framework, and the open circles represent gas loading in the rigid framework. We see that as pressure increases, the framework rearrangement causes a significant increase in gas loading, represented by the divergence of the solid and open circles. Comparing the orange line, representing methane, and the blue line, representing carbon dioxide, we see that framework rearrangement has a greater impact on carbon dioxide adsorption than methane adsorption. Throughout the study, we found that gas loading increases with gas pressure. Of the three polymers, gas loading was highest in PIM-TMN-Trip, followed by PIM-TMN-SBI, and then PIM-1. Then we compared the loading of different gases in PIM-1, and PIM-1 shows the highest loading of carbon dioxide and of gas mixtures containing carbon dioxide relative to other gas mixtures, suggesting that PIM-1 preferentially absorbs carbon dioxide. Our comparison of GCMC and MCMD simulations show us that framework rearrangement plays an important role in calculated gas loading. In the future, we will simulate gas mixtures in each of the polymers in order to calculate selectivity for industrially relevant gas mixtures. We will also use MCMD techniques to evaluate gas loading and selectivity, allowing us to take into account the effects of framework rearrangement on gas loading. We will additionally carry out a detailed framework restructuring analysis for gas mixtures to assess how mixed gas framework restructuring affects selectivity. I would like to thank the members of the Kalina Research Group, particularly Dr. Karai Kalina and my mentor, Dylan Anstein, as well as my funding sources. Thank you for watching, and go Gators!